Hi, I'm the Wannabe Coder, and welcome back to the Pac-Man and Python series. This is episode 5, and in this one, we're going to add one of the most important mechanics in the game, wall collision detection. Up to this point, Pac-Man can move freely around the maze, but he doesn't care if he's walking through walls. So now, it's time to give him some awareness of his environment. To do this, we'll write a function that checks if Pac-Man is about to move into a wall. And if he is, we'll simply block that move. But first, a quick recap. In the last episode, we created Pac-Man in a new file called actors.py. We started by building a general actor class to handle shared setup and drawing logic, and then created a player class that inherits from it and adds movement behavior. We also added wraparound logic, so Pac-Man can move off one edge of the screen and reappear on the opposite side, just like in the original game. With Pac-Man now active and moving, it's time to teach him how to interact with the maze, starting with wall collisions. To implement the collision detection, we're going to add a new method to the player class, and we're doing it inside actors.py. Now you might wonder, why not put this logic in main.py, since that's where the game loop lives? That's a fair point, and honestly, that could work too. But since we already defined the player's movement and behavior inside the player class, it makes sense to keep related logic together. Let's switch over to actors.py and start building it. We're going to define a new method inside the actor class. This will help clean up the heading values of any actor. We type def get underscore heading, open parentheses, self-close parentheses. Inside this method, we calculate the current direction the actor is facing, but we make sure it's clean and accurate. The Turtle library uses floating point numbers for directions. So, for example, instead of returning exactly 90, it might return 89.999. These tiny decimal values can cause problems when we compare directions in our collision logic. So here's what we do. We take the result of self.heading, which gives us the actor's current angle, and then we round it using the round function. This gives us a clean whole number, like 0, 90, 180, or 270. Finally, we return that rounded number. In Python, the word return means we give back a value from a function so that other parts of the code can use it later. In this case, get underscore heading returns the cleaned up angle, which makes our direction checks much more reliable. Now we need to give the player access to the wall coordinates. To do that, we add a new parameter to the player's init method. This new parameter, called walls, represents a list of all the wall tile positions in the maze. Inside the method, we store it using self.walls equals walls. This saves the list as an attribute of the player, which means the player can now check where the walls are during gameplay. Later on, when we create the player in main.py, we'll need to pass this wall list into the player as an argument. Right now, we're just preparing the player to receive it. We'll update main.py soon to make that connection. But before we go over the code line by line, let's take a moment to understand the logic behind our collision system. Here's the idea. When Pac-Man is moving, for example, to the right, we want to check if his right edge is about to enter a wall. And we do the same for every direction. If he's going left, we check the left edge. If he's going up, we check the top. And if he's going down, we check the bottom. Now remember, Pac-Man is always centered on the grid. If each tile is 30 pixels wide and Pac-Man is sitting right in the middle of a tile, then his edge, whether it's left, right, top, or bottom, is exactly 15 pixels away from his center. That's what we call cell size divided by 2. So when we say, check if Pac-Man's edge is inside a wall, what we really mean is this. Take Pac-Man's center position, add half a tile in the direction he's moving, and then check if that point overlaps a wall tile. Let's go through some examples. If Pac-Man is moving right, we take his X position, add cell size divided by 2, and check if that spot is inside the wall's horizontal area. If he's moving left, we subtract cell size divided by 2 from his X position and check if that point is inside a wall. The same logic applies for vertical movement too. If he's going up, we check his top edge, and if he's going down, we check the bottom edge. In every case, we're just asking, is the leading edge of Pac-Man, the furthest point in his current direction, overlapping a wall? If it is, we move him one tile back so he ends up just outside the wall, not inside it. Then we set his state to stop so he won't keep trying to move forward on the next frame. Now that the logic makes sense, let's go over the actual code that handles it. We define a method called check_wall_collision with self in parentheses and a colon at the end. Inside the function, we write round_x equals round, open parenthesis, self.x, CEOR, with empty parentheses, then close parenthesis. Then round_y equals round, open parenthesis, self.y, CEOR, also with empty parentheses, then close parenthesis. This gives us Pac-Man's current x and y positions, rounded to whole numbers, so they stay perfectly aligned with the grid. Next, we write heading equals self.get_heading with empty parentheses. This uses the getHeading method we defined earlier in the actor class, which returns the angle our player is currently facing, rounded to the nearest whole number. That means the result will always be one of four values: 0, 90, 180, or 270, representing right, up, left, and down. Then we write half_cell equals round, open parenthesis, cell_size divided by 2, close parenthesis. This gives us half the size of a tile, usually 15 pixels, and we round it to avoid floating point issues. We'll use this value to calculate the edges of Pac-Man when checking for collisions. Next, we write for x, y in self.walls, followed by a colon. This starts a loop that goes through every wall tile in the maze, so we can compare Pac-Man's position to each one and check for collisions. The variable self.walls is the list of wall coordinates that we stored earlier as an attribute of the player. It contains the center position of every wall tile in the maze. Inside the loop, we write dx equals round_x minus x, and on the next line, dy equals round_y minus y. These two variables represent the distance between Pac-Man and the wall we're currently checking, measured separately in the x and y directions. So, dx tells us how far Pac-Man is from the wall horizontally. If it's 0, that means they're perfectly lined up in the x direction, and dy tells us how far Pac-Man is from the wall vertically. Again, if that value is 0, it means they're aligned in y. We'll use these two numbers to figure out whether Pac-Man's edge, in the direction he's moving, is close enough to hit this wall. We start with, if heading equals 0, colon. This checks if Pac-Man is currently moving right. Then, inside that block, we write, if minus half cell is less than dx plus half cell, which is less than half cell, and minus half cell is less or equal to dy, which is less or equal to half cell, colon. Let's break that down. Heading equals 0 means Pac-Man is facing right, so we're checking if there's a wall directly in front of him. We already calculated dx as round_x minus x, which gives us the horizontal distance between Pac-Man's center and the wall's center. Then we add half a cell to dx, which gives us the position of Pac-Man's right edge relative to the wall, and we check that edge, not just the center, because a collision happens the moment Pac-Man's front touches the wall, not when his body is already halfway inside it. So this check gives us precise timing for when to stop. Next, we check if that edge is greater than minus half a tile and less than plus half a tile. If that's true, it means Pac-Man's right edge is overlapping the wall's horizontal space. This means we have a collision. At the same time, we also check if dy is greater than or equal to minus half cell and less than or equal to half cell. This tells us that Pac-Man is aligned vertically with the wall. He's not too far above or below, and this check is important to make sure we're only detecting walls that are on the same row as Pac-Man. Now here's why the or equal matters. Let's say Pac-Man's center is aligned exactly with the top edge of a wall that's below him, or the bottom edge of a wall that's above him. That would mean dy is exactly equal to plus or minus half a cell. If we didn't include the equals, this check would fail, and Pac-Man will end up slipping into a wall. By using less or equal, we make sure that a collision is still detected even when Pac-Man's center is lined up exactly with the edge of the wall, so there's no tiny gap where he could slip through. With both of these conditions, we're confirming that Pac-Man is in front of a wall, and close enough to trigger a collision. So, if both conditions are true, we write self.setX, open parenthesis, x minus cell underscore size, close parenthesis. This moves Pac-Man one full tile to the left, placing him right next to the wall, so his right edge no longer overlaps it. Then we write self.state equals stop in quotes. This tells Pac-Man to stop moving, so he doesn't keep trying to push into the wall on the next frame. Now let's check the left side. L if heading equals 180, colon. This means Pac-Man is currently moving left. Then, inside that block, we write, if minus half cell is less than dx minus half cell, which is less than half cell, and minus half cell is less or equal to dy, which is less or equal to half cell, colon. Let's break that down. Heading equals 180 means Pac-Man is facing left, so we're checking if there's a wall directly to his left side. Then we subtract half a cell from dx, which gives us the position of Pac-Man's left edge relative to the wall. We check if that left edge is greater than minus half a tile and less than plus half a tile. If that's true, then Pac-Man's left edge is overlapping the wall's space and he's close enough to collide with it. At the same time, we also check if dy is greater than or equal to minus half cell and less than or equal to half cell. Just like before, this confirms that Pac-Man is vertically aligned with the wall and helps us ignore walls that are too far above or below. This makes sure we only react to walls that are on the same row Pac-Man is currently on. If both checks pass, we've got a collision. To fix it, we write self.setX, open parenthesis, x plus cell underscore size, close parenthesis. This moves Pac-Man one full tile to the right, so he's just outside the wall and no longer overlapping. Then, self.state equals stop in quotes. We stop his movement to prevent him from trying to go further into the wall. Now we check. Elif heading equals 90 colon. This means Pac-Man is moving up. Then we write, if minus half cell is less or equal to dx, which is less or equal to half cell, and minus half cell is less than dy plus half cell, which is less than half cell, colon. Let's break that down. Heading equals 90 means Pac-Man is going up, so we're checking for a wall above him. This time, we check if dx is within half a tile to confirm he's horizontally aligned with the wall. Then we calculate dy plus half cell, which gives us the position of Pac-Man's top edge relative to the wall. We check if that edge is within the wall's vertical space. If both conditions are true, we write self.set y, open parenthesis, y minus cell underscore size, close parenthesis. This moves Pac-Man down by one tile, so his top edge is placed just under the wall. Then we write self.state equals stop to prevent him from continuing to move upward. This follows the same structure as the horizontal collision checks. We're just switching x and y in the logic, since we're now checking movement in the vertical direction. Finally, we check L if heading equals 270 colon. This means Pac-Man is moving down. Then we write, if minus half cell is less or equal to dx, which is less or equal to half cell, and minus half cell is less than dy minus half cell, which is less than half cell, colon. Heading equals 270 means Pac-Man is going down, so we're checking for a wall below him. We confirm he's horizontally aligned by checking dx and then calculate dy minus half cell to get the position of his bottom edge relative to the wall. If that edge falls within the wall's vertical space, we stop Pac-Man by moving him one tile up and setting his state to stop. Alright, before we move on to the rest of the collision function, let's switch over to main.py and get it working in the actual game. First, we need to make sure the collision function is called during gameplay. To do that, we go to the game loop. This is the function that runs the game logic over and over. Inside the loop, we add player.check_wall_collision with parentheses. This tells the game to check for wall collisions every frame. Since the game loop runs about 60 times per second, Pac-Man will constantly be checking whether he's hitting a wall. We call this after the move function, so the collision logic can check Pac-Man's new position and stop him if he just entered a wall. This makes collisions feel smoother and more accurate on screen, without any jumpy or delayed reactions. Now for the collision to actually work, the player needs access to the list of wall coordinates. So let's scroll down to the main function. After we draw the walls, we store their coordinates by writing walls equals wall_pen.walls. Just as a reminder, this works because inside the wall class, we stored the list of wall coordinates in an attribute called walls. So here, we're simply accessing that attribute after calling wall_pen.draw. This gives us a full list of every wall tile in the maze, each one stored as a coordinate pair, like x, y. Next, we pass that list into the player class. Player equals player, open parenthesis, walls, close parenthesis. This gives the player everything it needs to detect and react to collisions properly. Now let's run the file and test what we've got. We should see Pac-Man moving around the maze and stopping when he hits a wall, just like we expected. The collisions feel solid and responsive, and he no longer slides into or through wall tiles. But if you look closely, you might notice a small issue, especially when Pac-Man is near corners. Sometimes he'll get stuck, even though it looks like there's a clear path in front of him. Or he might clip into a wall if he's just slightly misaligned on the grid. That's because our current logic only checks for direct head-on collisions, and only when Pac-Man is perfectly aligned with the wall. It doesn't help if he's just a few pixels too high or too low, and it doesn't correct him when he's trying to make a tight turn. That's where our next conditions come in. We're going to add a couple of extra checks right after the main collision condition to handle two things. First, they prevent Pac-Man from slipping into walls if he turns while slightly misaligned. For example, imagine Pac-Man is moving down and you press the right arrow to turn into a hallway. If you press the turn just a little too early or late, Pac-Man might start turning before he's perfectly lined up with the new column. Without a correction, he could brush the corner of a wall and slide into it, which looks glitchy and breaks the clean grid feel. Second, they help Pac-Man snap into place when he's trying to make a valid turn, but his position is just a few pixels off. If the turn is technically allowed, but Pac-Man isn't quite aligned with the open path, the game might ignore the input or make the movement feel stiff. These new conditions fix both issues. They gently snap Pac-Man into position, nudging him to the center of the row or column he's trying to move into. That way, he can't drift into walls, and his turns feel smooth and responsive, just like in the original arcade game. Now that we understand what they do, let's go back to the code and read them line by line. Let's go back to our check wall collision function and look at the next two lines for when Pac-Man is moving right. These are the correction lines we talked about earlier. We start with L if minus half cell is less than dx plus half cell, which is less than half cell, and dy is greater than half cell, and the absolute value of dy is less than cell underscore size colon. Then we write self.set y open parenthesis y plus cell underscore size close parenthesis. Here's what's happening. The first part, dx plus half cell, checks if Pac-Man's right edge is already inside the wall tile on the x-axis. The second part, dy greater than half cell, means Pac-Man's center has passed the top edge of the wall, so he's slightly above it. and abs dy is less than cell underscore size ensures that the wall is still within one tile vertically, which means it belongs to the row below the open path Pac-Man is trying to enter. So this condition handles the case where there's a wall just below Pac-Man and he's trying to turn right into an open path above it, but he's not perfectly aligned with that row yet. Since his right edge has already cleared the wall, the turn is allowed, but his Y position is slightly off. To fix that, we snap him up by one tile, by setting his Y position to Y plus cell size. That places him directly above the wall, aligned with the center of the open tile he's trying to turn into. This gently realigns Pac-Man so he can enter the new row cleanly without hitting the corner of the wall. The next line does the same thing, but in reverse. We write L if dy is less than minus half cell, which means Pac-Man's center is below the wall's center, so the wall is above him this time. Then we write self dot set y, open parenthesis, y minus cell underscore size close parenthesis. This corrects Pac-Man's position when he's trying to turn right into a path below a wall, and he's not yet aligned with the new row. These two corrections work in two key ways. They help Pac-Man snap to the correct row on the grid when he's close to making a valid turn, and they prevent him from accidentally entering a wall when he's not vertically aligned. That way, even if the player turns a bit early or late, the game gently realigns Pac-Man, and the turn feels smooth and responsive, just like in the original arcade game. Now let's look at the correction lines for when Pac-Man is moving left. We write L if minus half cell is less than dx minus half cell, which is less than half cell, and dy is greater than half cell, and the absolute value of dy is less than cell underscore size, colon. Then, self dot set y, open parenthesis, y plus cell underscore size, close parenthesis, and just after that, L if dy is less than minus half cell, followed by self dot set y, open parenthesis, y minus cell underscore size, close parenthesis. The rest is the same as before. These lines follow the same logic we used when moving right, just applied to the left edge of Pac-Man instead. If he's slightly too high or low while trying to turn into a new row on the left, we snap his Y position up or down to realign him with the open path. This keeps movement clean and precise, especially when turning near walls. Now for the vertical directions, up and down. These correction lines follow the same idea, but this time we adjust Pac-Man's X position to snap him into alignment with the correct column. When moving up, we check if Pac-Man is too far left or right while entering a new path, and use set X to nudge him into place. Same thing for down. We check his horizontal offset and correct it by moving him left or right by one tile. This keeps Pac-Man centered in the grid when turning into vertical paths, and avoids any awkward misalignment at vertical junctions. Now let's go ahead and run the file to see what's changed after adding all those correction lines. You should notice a big difference, especially when turning near corners. Pac-Man no longer misses turns just because he was slightly off-grid, and he doesn't slide into walls when turning late. Instead, his position is gently corrected, so even slightly early or late turns feel smooth and responsive. This gives us that snappy, arcade-style movement that makes Pac-Man feel polished and fun to control. Let's quickly recap what we've done so far. We added basic collision detection to stop Pac-Man when he hits a wall. Then we took it a step further, adding corner correction logic to gently snap Pac-Man into alignment when he's turning near edges. Now Pac-Man can move smoothly through the maze, stop at walls, and turn cleanly into any open path, even if he's slightly off-grid. So what's next? It's time to start building the user interface area. We'll draw a section at the top of the screen to display the score, and eventually, lives and game status. We'll also start working on pellet collection, which means clearing pellet stamps whenever Pac-Man eats them. This will let us track the player's progress and eventually connect it to scoring. If you found this helpful, a like and subscribe would really help support the channel, and make sure you don't miss what's coming next. I'm the Wannabe Coder. Thanks for watching, and I'll see you in the next episode.